Hello, everyone, and welcome back to another MECH 220 video series. Today we'll be covering Chapter 20, which is General Motion in 3D. Specifically, we'll be covering example 20-4 from section 20.3. So let's go ahead and read the problem. The ladder of the fire truck rotates around the z-axis with an angular velocity of 0.15 rad per second, which is increasing at 0.2 rad per second squared. At the same instant, it is rotating upward at 0.6 rad per second, while increasing at 0.4 rad per second squared. Determine the velocity and acceleration of point A, located at the top of the ladder at this instant. So what I've done already here is redrawn the problem in a simplified way, sort of getting rid of things that aren't really necessary to the evaluation of the problem. So I have drawn this arrow here, which represents the ladder, which is R of A with respect to O. We'll get to that later. Also, the velocity and acceleration of Z, omega 1 and omega 1 dot, from which we have, and then the rotation of X with omega 2 and omega 2 dot, which also we have. I've also written down a few notes here that are important, really, to this whole section of the course. For starters, the order of rotation does matter in 3D, um, and it matters mostly when you're solving for angular acceleration, which I have sort of written out a pattern for you here, which we'll cover further down in the problem. And then lastly, I have the sign rule for cross products because, well, in 3D motion, you'll be doing a lot of cross products, so I find it useful to have that there. So the next thing that I'm going to do is I'm going to just write out the equations for velocity and acceleration of A with respect to O, because that's what the problem is asking for. Right, so our point O here, which is a known point that we have, is completely fixed. It's not moving, it's not accelerating, so immediately we can say that the velocity of point O is 0 and that the acceleration of point O is 0. Now that we have our problem set up, let's start solving for velocity. I'm just going to rewrite my equation here, excluding the velocity at 0. So the rule in 3D motion is that the angular velocity of the rigid body is equal to, well, in this case, which is equal to the angular velocity of the ladder, which is the angular velocity of A with respect to O, is the sum of the angular velocities. So we're just going to go ahead and compute that right away. Our first angular velocity is 0.15 k hat, because this is a vector addition, and omega 1 is rotating about the z-axis, so we assign the k vector to it, the k unit vector to it, plus 0.6 I hat, and that's in rad per second. Next thing we need is R of A with respect to O. This is essentially this length here, this vector there. which represents the ladder. So that can be found doing a simple trig, since, as I mentioned earlier, AO is within the ZY plane. So that's just 40 cos 30J plus 40 sine 30K hat. And that is in feet. So we have all of our variables. We're just going to go ahead and plug that in to velocity. I'm not going to do the cross product right here because this is quite a long problem. But if you do the cross product yourselves, you will find that this will be your answer. And that's in feet per second squared. Right. So we're just going to highlight that. And that is part 1 of our problem done. So now time for acceleration. Like we did for velocity, I'm just going to rewrite our equation for acceleration. Right off the bat, you'll notice that this is essentially the same thing as your velocity at A. This isn't always the case. For example, if ever you're in a situation where the velocity at your origin or whatever point you're taking it from is not 0, then, well, this is simply not true. But because it is 0, it just so happened that it's the same thing as this. And it's nice because, well, you have one less cross product to do. Right, so if you look at our expression, immediately we know that we have this, we do not have angular acceleration. And that's what we have. So another thing you'll notice from this expression right off the bat is that we know this value because we computed it in velocity. We also know this value because, well, we computed it finding velocity. What we don't know is the angular acceleration of the latter, and that's the next thing that we have to find. And this is actually where it gets tricky, simply because it doesn't work the same way as velocity. And it has everything to do with the note and has everything to do with the note that I wrote down at the start of this problem. So, unlike for angular velocity, the the angular acceleration of the body is not equal to the sum of the angular accelerations. And this is because any subsequent accelerations that are happening within rotating reference frames. And so the way we represent that here is with this expression. And I've written omega 1, omega 2, omega 3, dot, 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 just so you can see the pattern, because essentially we'll follow this pattern um, pretty much every time. So you'll notice that omega 1 dot here is the only one that's standing alone, and that's because it's your base acceleration. It's not within any rotating reference frame, it just exists on its own. And you'll notice for omega 2, suddenly we have all these extra and omega 3 dot and omega 2. But here, for omega 2 dot, omega 3 dot, we're starting to include all these subscripts. That's because omega 2 dot and omega 3 dot, they're rotating within a rotating reference frame, which is omega 1. So what we do to compensate for that is that we add this extra term here, omega 1 cross omega 2, and omega 1 plus omega 2 cross omega 3. Now, what this represents is the rotating reference frame. And the reason why, with every subsequent um, acceleration or velocity, you're adding the two together like this. And that's because if you look at it situationally, um, your third acceleration, your third angular acceleration is happening within the first rotating frame and within the second rotating frame. So if I apply that logic to the ladder here, we have the base that's rotating, and then we have the ladder that's accelerating within that first rotation. And this is how we're going to use this expression to solve the problem. So we have omega 1 dot, which we know, omega 2 dot, which we also know, plus omega 1 cross omega 2. And when I said that we knew omega 2 dot, it's because we actually know it. Um, in this case, our rotating reference frame and our fixed reference frame, well, they're all the same. Usually, that will be the case. Either a rotating frame will have the same origin as your fixed reference frame, either the axes will be completely collinear, as in this case, or you will have parallel axes. In this case, it's within the same frame, so the value here that we got for the second angular acceleration, 0.4 rad per second, we can go ahead and just plug that in. And that's what we're going to do right now. So we have 0.2k plus 0.4 I plus 0.15 k cross 0.6 I. if you compute that cross product, you will get 0.2 k hat plus 0.4 I hat plus 0.09 j hat. And all of that is in rad per second squared. All right, now that we have found all of our terms, we can go ahead and plug that in to our equation for acceleration. All right. Um, if you can do all of these cross products, you should get this as your final answer. And I really suggest that you take your time with the cross products when you're practicing them, because if you don't sort of get a strong base with that when you're in an exam situation and, well, when you don't have the luxury of time, it can get a little overwhelming. So just take your time with that. And yeah, here's your final answer for acceleration. And that's the end of this problem. One thing I would like to mention, the sign convention for these velocity and accelerations, um, because obviously we're not working with scalar values, we're working with vectors and we're doing vector additions and we're doing cross products and such. So here in the problem, both of these rotations are happening in the counterclockwise direction, and do like based on the sign convention, counterclockwise is greater than 0 and clockwise is less than 0, which is why that when we're calculating all of these, um, doing all these vector additions, all these values were positive. All right, and that's it. Thank you for listening.